Okay, so I'm Jacob, this is Jordan, and our math branch was analysis. And analysis covers a few different topics, calculus, and we're going to talk a little bit about differentiation and integration in that regard. And then vector analysis and differential equations are also what we'll be talking about. Calculus originated really a long time ago when just the roots of it started being formed. It started off with the Greeks, and they did really just basic things. They didn't actually do calculus like we do today, but here's a few names of the mathematicians who worked on those. And Archimedes, as I think was in a previous presentation, did something on finding the value of pi with it using sort of like a very rudimentary calculus to find pi. And then it really didn't have any more advancements in the field until the 1600s after the Greeks. And then here's just a few of the names in it, and then we're going to focus more on Newton and Leibniz. So both these guys discovered calculus individually, and here's Newton and there is Leibniz. Newton did discover it first. He finished up his original works in 1666, but he didn't publish his findings right away. And part of these works were the fundamental theorem of calculus. He used derivatives and integration. He called them fluxions, and then he also did a lot of work in series. And Newton wasn't so concerned about what his notation was, since he wasn't publishing it. He kind of just used his own thing. Whereas Leibniz, who actually started working on calculus in 1673. Both these dates are supposed to be 16, not 19. And he published it in 1684, and he thought of it as x and y both changing at various rates at just infinitesimally small changes, and thought of integration as a sum, as most of us were taught to. Integration is the sum under a curve, and he, unlike Newton, took really careful notation, and that's the notation we use today: dx, dy, integral, all that stuff is from Leibniz. And then here's the fundamental theorems of calculus, as I'm sure we all know. These are from Newton, and I think all of us have seen these before.
So differentiation is just part of calculus, and just the most simple way to put it is just tell how fast something's changing. To differentiate, you just have to find the derivative of a function. And to do that, it's just a change in displacement, or just how much something changed over the change in time. And the easiest, most simple way to look at that is just, on the example, is how fast water is being poured out of a bucket. So if you poured a bucket and there was this much water in there, and you poured it for 5 seconds and so much was out of it, you would put how much changed over the amount of time, and then that would be your derivative. There's a lot of different techniques to find the different derivatives, and all these are just different rules that are on there. And that's just a couple of them. When most of you guys did when I first did calculus, we were actually given a sheet with all these rules on there, and then they'll come in, they'll help out a lot. So you don't have to remember all the different rules, because you bring in the trigonometric rules for sine, cosine, all those. And that website is just a more complete set of all the rules and different tips and tricks to have to go through them. So integration it's another branch out of calculus, and just like I said, it helps you find a function whose derivative is equal to a function that was already given to you. And when I first took calculus, Mr. Strand, he said the easiest way to think of it is just the opposite of differentiation. It is used to find the area under a curve of a function, and that's just this is the most basic. You can go go up to like double, triple integrals, and you just add more, like it just goes into deeper dimension.